Chapter 2, Section 2, Digging Deeper, Igneous Rocks, the Nature of Igneous Rocks. In the Investigate, you first looked at the properties of igneous rocks and how they can be classified. Then, you used a geologic map to locate these rocks in your area. Finally, you gathered information about the environments where igneous rocks form. All igneous rocks are made of interlocking crystals of minerals. In fact, all rocks are made of minerals. The minerals have cooled and crystallized out of magma. Recall that magma is molten rock. The way the crystals grow together and their composition makes igneous rocks very resistant to physical weathering and erosion. As you read in Section 1, minerals are usually made up of several chemical elements. Each mineral has a specific chemical makeup and crystal structure. Each mineral has a chemical formula. The chemical formula shows the amount of the various chemical elements in its makeup. There are thousands of kinds of minerals in Earth's crust. However, only 6 are common in igneous rocks. They are quartz, feldspars, micas, pyroxenes, amphiboles, and olivines. These are all called silicate minerals. These are all called silicate minerals. Their basic structure is very tightly bonded units made up of silicon and oxygen called silica. These units are bonded less strongly to various other atoms. Of the 6 kinds, all but quartz vary widely in chemistry, even though the basic nature of the mineral is the same. For example, plagioclase and potassium are 2 kinds of feldspar. They have slightly different structures and very different chemical makeups. Muscovite and biotite are 2 kinds of mica. Muscovite and biotite are 2 kinds of mica. Again, both have slightly different structures, but very different chemical makeups. Magma, lava, and igneous rock. Igneous rocks are formed from the cooling of magma. Suppose that you could drill a hole very deep into Earth. You would find that Earth's temperature initially rises by about 30 degrees centigrade with every kilometer of depth. This rate of increase slows down at deeper depths. At a depth of 100 to 350 kilometers, the temperature is high enough for large volumes of rock to melt and form magma at certain times and places. Nearly all substances expand when they are heated. When rock is melted into magma, its volume increases by about 10%. This makes the magma less dense than the surrounding rock. Like a hot air balloon that rises through less dense surrounding air, magma rises towards Earth's surface. See Figure 1. Okay, so I'm going to scroll down to Figure 1 so that as I'm talking about this, you can refer to Figure 1. All right, there we go. Some magmas cool and solidify into igneous rock before they reach the surface. The rock that forms in this way is called intrusive igneous rock. The magma intrudes into solid rock that was already there. In some places, magma reaches the surface before it solidifies into igneous rock. Magma that reaches the surface is called lava. Rock that is formed when lava cools is called extrusive igneous rock. The lava is extruded onto Earth's surface like toothpaste from a tube. As you will see, the appearance of an igneous rock reveals whether or not it was formed. As you will see, the appearance of an igneous rock reveals whether or not it was formed below or at Earth's surface. Figure 1 is a cross-section of a subduction zone showing the locations of igneous rocks that form by the solidification of minerals from cooling magma in various settings. Seafloor spreading typically produces igneous rocks that are closer in composition to the mantle asthenosphere compared to those in continental crust produced by partial melting. So there's a mid-ocean spreading ridge, ocean crust, which is mainly basalt and gabbro. There's the mantle lithosphere, mantle asthenosphere, partial melting, continental crust, volcanoes, volcanic rock, which ranges from basalt to rhyolite, and accretionary wedge. So, like they said, as the rock, the further towards the center of the earth the rock is, the hotter it is, which makes it melt, which makes it less dense, which makes it expand and begin to lift. And that's where you get the volcanic eruptions from all the pressure building up. All right. Classifying igneous rocks by texture. The crystal size of an igneous rock largely depends on how fast the magma cools. When magma cools very slowly, only a small number of crystals are formed in a given volume of the magma. However, these crystals have plenty of time to grow large. The resulting igneous rock is coarse-grained. The mineral grains are usually several millimeters or even a few centimeters in size. See Figure 2, right here. On the other hand, when magma is extruded at Earth's surface and cools very rapidly, a large number of crystals are formed in a given volume of the magma. However, there is not enough time for them to grow large. The resulting igneous rock is very fine-grained. The mineral grains are usually too small to be seen without a magnifying glass. If the lava cools even more quickly, a glassy textured rock called obsidian can form. Obsidian forms when magma cools so quickly that crystals do not have time to form. And there's Figure 2, granite with coarse grain texture. Figure 3, granite with medium grain texture. Classifying igneous rocks. I'll scroll up a little bit because it's showing igneous rocks as we're talking about this. That's granite. Classifying igneous rocks, chemical and mineral composition. The color of an igneous rock is due mainly to its chemical makeup. Therefore, the color depends on what minerals the rock contains. Think of the common minerals found in igneous rocks. Quartz, potassium, feldspar, and muscovite mica are light in color. Igneous rocks with high percentages of these minerals tend to be light in color. They are the most common minerals in igneous rocks found in the continental crust. Pyroxenes, amphiboles, plagioclase feldspar, biotite mica, and olivines are darker in color. Igneous rocks with high percentages of these minerals tend to be dark in color. Igneous rocks that consist mostly of minerals such as quartz, potassium, feldspar, and muscovite mica are lighter in color. This is because these minerals contain a lot of silica, silicon and oxygen. They contain little iron and magnesium. Igneous rocks containing these minerals are usually white, light gray, or pink. These rock types, whether intrusive or extrusive, are associated with lithospheric plates. They are found where the plates are moving together and magma is formed. Magmas rich in silica do not flow very easily. They usually cool before they reach Earth's surface, forming granite. Granites found at Earth's surface today formed below the surface long ago. They have been exposed by uplift and erosion. Uplift is the slow raising of the crust by large-scale forces acting within Earth. You will read more about this in a later section. If the same magma reaches the surface, it cools quickly. It forms an extrusive igneous rock called rhyolite. Igneous rocks that contain minerals rich in iron and magnesium, olivines, amphiboles, pyroxenes, and biotite mica, are dark in color. They are typically black to dark green. One extrusive igneous rock of this kind, basalt, is the most common rock on Earth's surface. It is the major rock found in the oceanic crust. Basalt is formed where lithospheric plates are spreading apart. Here, magma is rising through a mantle hotspot. These rocks are common in the Hawaiian Islands and Iceland. Gabbro is an intrusive igneous rock that contains minerals rich in iron and magnesium. It is the coarse-grained counterpart of basalt. It is common deep in the oceanic crust. Here's classification of igneous rocks that you can either pull from the PDF or you can take a screenshot of this video right now and kind of crop it to, you can kind of crop the sides of it. But okay, so how do we classify igneous rocks? So if the lighter rocks, and then there's the percentage of quartz they contain, and then here's some different types of light igneous rocks: granite, pegmatite. Here's different classifications as far as texture. You're measuring the crystals. Again, intermediate. So you're looking at the color. Light colored, intermediate colored, dark colored, very dark. You can classify them that way. But then you can also classify them by texture, by measuring the size of the length of the crystals. Now it might all just be just one big crystal like this, like obsidian, where it's literally just like a black sheet of glass. So then you wouldn't be measuring crystals. It wouldn't have any type of a bumpy or rough texture. It would just be a sheet of black glass, which is obsidian. A frothy igneous rock would either be pumice if it was light or intermediate. If it was frothy and dark, then it would be scoria. So it's an interesting way of, that is the way of classifying igneous rocks. Okay. All right, guys. Some igneous rocks are mixed in chemical makeup. These rocks are made of a mix of minerals that contain iron and magnesium. As a result, they are also mixed in color. Two examples are andesite and diorite. Andesite is an extrusive rock. Diorite is the corresponding intrusive rock. Andesite is named for the Andes Mountains. It is abundant in that area. Diorite often forms where an oceanic lithospheric plate is being subducted beneath a continental lithospheric plate. Water rising up into the mantle from the downward moving plate causes some of the mantle rock to melt. The magma rises up through the continental plate. There it melts some of the continental rocks, causing it to have a mixed makeup. So now we're talking, okay, so before we were talking about just classifying igneous rocks by color, by how light or dark they are, by their texture, some of which were rough, where you could actually feel the crystals and see the crystals, some of which were very smooth, where it was just all one glassy surface. Now, what's another way of classifying? Well, that was the classification. Now we're talking about igneous rocks in the crust. All right. So within the crust of the Earth, 10% is made up of granite, 11 diorite, 43% basalts, 0.2% peridotites, 0.8% others. Okay, so what's the total then? So you add all of the percentages up here, and the total igneous rocks, so talking about the Earth's crust and how much of the Earth's crust volume is igneous rocks, 65%. All right. So we went through that. I believe we went through all this section. Now or all of the subsection. Now we're on explosive volcanic eruptions. Some magmas have a high content of dissolved gases, such as water vapor and carbon dioxide. This is especially true of magmas with high silica content. When these magmas rise up near the Earth's surface, the dissolved gases tend to bubble out of the magma. Look, you can see that here. You can see where the gases bubbled out, but we'll get to that in a little bit. This happens because the pressure is so much lower at the surface than deep in Earth. Sometimes the pressure is released suddenly by an explosive volcanic eruption. This was the case at Mount St. Helens in the Pacific Northwest in 1980. The products of such an eruption are pieces of mineral grains and broken igneous rock called volcanic ash. In one sense, the rock formed from volcanic ash is a sedimentary rock because it is formed by the deposition of material. You will investigate sedimentary rocks in the next section. However, because it came directly from a volcano, it is usually considered to be an igneous rock. Pumice is a volcanic rock that consists mainly of bubble holes. There are only thin walls between the holes. Because of its very low density, pumice floats on water. Figure 4 shows a pumice sample from Mount St. Helens. Pumice has an irregular or frothy texture. Okay, so this is what a frothy texture looks like. So when we refer back up to this chart, there are two igneous rocks that have a frothy texture. One of them is pumice, which is light, and another one is scoria, which is darker. So now we know what that frothy texture is. Okay. Igneous rock units. A rock unit is a body of rock composed of the same type of rocks. Igneous rock units vary greatly in size and shape. They form either below or at the surface, as shown in figure 5. Okay. Batholiths are extremely large subsurface units that form from bodies of magma that have cooled and crystallized. They have irregular shapes and are composed, batholiths, which what they're referring to here. They have irregular shapes. They have irregular shapes and are composed of coarse granitic rocks. Sills are long sheets that intrude between layers of sedimentary rocks. Dikes are steeply angled and cut through existing rocks. Extrusive igneous units form at Earth's surface. Stocks occur when the magma in the vent of a volcano cools and solidifies. Lava flows occur when magma reaches the surface and cools to form fine-grained igneous rocks. In some places, intrusive igneous rock units can be seen at the surface. This happens because the surface has slowly been worn down by weathering and erosion. As a result, these rock units become exposed. For example, sills are composed of resistant rocks, and when exposed, they can appear as long cliffs called palisades. Let me scroll up a little bit so we can describe this. So you have active volcanism and you have ancient volcanic features. So you've got a batholith, dike, sills, the stock with radiating dikes. Then you have your active volcanism over here. You've got your magma chamber, your conduit, volcano, ash plume, cinder cone, recent lava flows. So figure 5 shows both extrusive and intrusive igneous rock units can sometimes be seen at the surface because weathering exposes rock units formed deeper in the crust. Figure 6 shows the Sierra Nevada batholith. The Sierra Nevada batholith is a massive intrusive structure in California. Figure 7 shows dikes and sills cut through existing rocks.